So in this video, I'll be introducing a new use for induction proofs, which are divisibility or multiples of kinds of proofs, where you're sort of trying to prove that something, an expression, in our case, it's going to be n squared minus 1, is divisible by an integer or another expression. In this case, 8. So we're asked to prove that n squared minus 1 is divisible by 8 whenever n is an odd positive integer, i.e. n is the set of positive odd integers, so 1, 3, 5, 7, and so on. Okay, just a reminder, or actually, if you didn't know this yet, then I guess it's a definition. For something to be divisible by something else, so I'll write it more formally. We say that A divides B, and the sort of formal expression is A bar B, where this is a vertical bar that this just means divides. So you read this as A divides B, right? We say that A divides B if and only if, or this is an if and only if because it's a two-way statement. If and only if A divides B. So B over A is equal to M, where M belongs to the integers, the set of integers. Or people also write it as B is equal to AM. So for example, 2 divides 4. So 2 divides 4 because 4 over 2 gives you 2, which is another integer, so which belongs to the set of integers. So that's the whole idea behind divisibility. So in this case, when I say n squared is divisible by 8, what I really want to say, so my statement Pn is going to be, so it can either be n squared minus 1 is divisible by 8, like the question says, but if you want to write it more formally, then you can say 8 divides n squared minus 1. Okay, so this is what we're trying to prove. Obviously, when n is an odd positive integer. Okay, so let's start with the base case. So in this case, the smallest number that can be applied to Pn is, remember that n belongs to the integers and n is odd. Okay, so in this case, it's going to be n equals 1 because it's the smallest positive odd integer. So let's check that P1 is true. P1 is true. Well, let's see. N squared minus 1 becomes 1 squared minus 1, which is equal to 0. And when you take 0 and you divide it by 8, that gives you 0. Is 0 an integer? Yes, it is. So by the definition I just gave you here of divisibility, we can say that 0 is divisible by 8, or if you like, 8 divides 0, meaning that P1 is true. So I've proved my base case. Okay, now on to the inductive step. Now the inductive step, as always, is a bit trickier. So remember what I do in my inductive step. I am going to assume that Pn is true. I.e., I'm assuming that 8 divides n squared minus 1. I just write it with the bar because it's faster to write. That's the only reason. And remember, this is very key. N belongs to the integers, positive integers rather, and n is odd. So 1, 3, 5, and so on. Okay, so this fact is going to be important in my inductive step or inductive hypothesis, and you'll see why. So what I want to do in this case is, and now we have to be careful. Okay, so my goal is to prove Pn plus. Okay, now your reflex would be to write n plus 1, right? Because that's what you do in inductive proofs. In induction proofs, you say Pn is true and you prove for the following integer. But the thing is, if you assume that Pn is true, n is odd, right? Okay, n is odd. Okay, so for example, n can be, I don't know, n can be 7. Okay, so that's fair. N is odd. And now I'm saying that I'm proving for n plus 1. But what is n plus 1? N plus 1. Well, if n is odd, then the following integer is going to be even. N plus 1 is even. So in this example, n plus 1 is going to be 8. And 8 is not true. 8 is not true for Pn. Does not apply to Pn. Okay, so we can't use n plus 1. Okay, because that would be false. That would give me an even integer, and then my statement over here, this statement, would no longer be true. Like, it wouldn't be true that, well, actually, no. This would be true, but it wouldn't be true that Pn plus 1 is divisible by 8, because n plus 1 is not odd. Okay, as it says here. So what I need to do, I need to take the following integer, n plus 2. And n plus 2 is going to be odd. Because it's going to be 9 in this case. So this is sort of my example to illustrate. Okay, so rather than 1, I'm going to write n plus 2. So make sure you understand why I did n plus 2 and not plus 1. Because if I did n plus 1, I couldn't do my proof, because my statement would be wrong automatically, because I'm not proving for the right condition. Okay, so let's go ahead and try to solve for, well, to prove for n plus 2. So in a divisibility proof, what you do is you take your n plus 2, or you take your, usually it's going to be n plus 1, and you put it into your expression, so where the n is supposed to be. So in this case, n squared minus 1 becomes n plus 2 square minus 1. Okay? Now let's see what this becomes. So let's expand this. This becomes n squared plus 2n plus 1 minus 1. So automatically your reflex is to cancel, right? Is to cancel the ones, okay? In this case, don't do that. Don't cancel the ones, okay? Don't cancel the ones. And the reason why is because if you cancel the ones, then you're not going to be able to use your inductive step. Your inductive step is n squared plus 1. That's your inductive hypothesis or inductive step. So now I'm going to do my inductive hypothesis. I'm going to rearrange this. This is n squared minus 1 plus 2n plus 1. Okay. Actually, I think there might be something wrong. Yeah, this should totally be 4. So just don't cancel this one over here. So sorry about that. That was my mistake. Okay. And so what I have here now is I have n squared minus 1, which I know is divisible by, oh, but this changes everything. Yeah, my bad. This is all not right. So this should be n squared plus 4n plus 4 minus 1. Okay. Okay, now this looks right. Okay, so don't cancel your 1's over here. Okay, so now I'm going to rearrange. I'm going to say n squared minus 1 plus 4n plus 4. Okay, so this is my inductive step. Okay, so this I know is divisible by 8. So this is divisible by 8. Okay. Now what I want to show is I want to show that this is divisible by 8. Divisible by 8. Because if I'm adding two things that are divisible by 8, then for sure the whole thing is going to be divisible by 8. Okay. Right. So now what I want to do is show. I want to show that 4n plus 4 is divisible by 8. Okay. So how I'm going to do this? Is, well, I'm going to see, what I'm going to do is I'm going to say 4n plus 4 is equal to, I'm going to factor 4, n plus 1. Okay. And what I know now is that I've shown you before that n plus 1 is even, right? This is going to be even, okay? But if I multiply 4 by any even number, I'm going to get something that is divisible by 8, okay? Because I'm dealing, remember, I'm dealing with n belonging to the positive integers, right? So if n belongs to the positive integers and is odd, then, for example, n can be 1, right? So if n is 1, then 4 by n plus 1 is actually 4 by 2, which is 8. Or let's say if n is 3, then 4 by n plus 1 is just 4 by 4, which is 16, which is also divisible by 8. Right, so this can be divided by 8, this can be divided by 8, and so on. So let's do another one for 5. You'll get 4 times 6, which is 24, which is also divisible by 8, and so on. So you can see that because this is even, and I'm multiplying by 4, all of this is divisible by 8. Okay, so both of my expressions, my two expressions, n squared minus 1 and 4n plus 4 are divisible by 8. So if I'm adding, so what that means is I can rewrite n squared minus 1 as 8 times whatever constant k, right, where k belongs to the integers, okay? And I can write 4n plus 4 as, let's say, 8t, where t belongs to the integers. So this is because I know both expressions. I know both expressions are divisible by 8. So if something is divisible by 8, that just means that it's a multiple of 8, meaning that I can sort of rewrite it as 8 times something. Okay? So now this here is going to become 8k plus 8t, which you can see is 8 times k plus t. And so all of this expression is divisible. All of this expression is divisible by 8 because it has 8 as a common factor. Okay? So that means that, so n plus 2 squared minus 1 is divisible by 8. Therefore, p n plus 2 is true. And so what that means is I've proven that for any odd positive integer, n squared minus 1 is divisible by 8. Okay, so I've shown this with my inductive step. This actually might have been confusing. I'll just go over it just quickly. So I assume that Pn is true, so 8 is divisible by n squared minus 1. Remember that n is odd. Okay, so now I need to prove my next term, my n plus 1, or in this case my n plus 2 term. Remember why I used n plus 2, because n plus 1 is even, so it doesn't apply to my statement p. So, but n plus 1 does, and it's the following integer, or the following sort of n, it's the integer after n. And so I replaced my n here by n plus 2 squared minus 1. Then I opened it up. I made a mistake there, but I caught it, and so that's n squared plus 4n plus 4 minus 1. I rearrange this. Remember not to cancel your 1 here. And so I get n squared minus 1 plus 4n plus 4. This is divisible by 8 by my inductive step over here. And 4n plus 4 is divisible by 8 because you can factor that as 4 times n plus 1. N plus 1 is even, so 4 times an even number is automatically going to be divisible by 8. So I conclude that both of these things here, this and this, are divisible by 8. So I rewrite them. I rewrite them as factors of 8. And so I get 8k plus 8t, which I can factor an 8 from, so I get 8 times k plus t. And clearly this statement can be divided by 8 because it has an 8 as a common factor. And so n plus 2 squared minus 1 is divisible by 8, and I've shown my inductive step. So that proves that for any odd positive integer, n squared minus 1 is divisible by 8.